Hello, my name is Roman Samchuk. I'm head of engineering here at SDC Verifier, and I'm going to host this webinar today. The topic of the webinar is modeling FEA simulation for steel structures, standards, tools, and automation. Pretty long topic, so I hope to have an interesting discussion today. Before we getting started, something very important. Can you confirm that everybody can hear me and you can see my screen, which I'm going to share right now? Just a moment. Oop. Now we should be able to see my screen, and I hope you can hear me well. Yes, I can hear you. All right, thanks for confirmation. Couple of words. Whole webinar will be recorded, so those who registered but do not have chance for now to join this webinar, they have chance to rewatch it later. That's one thing. Second thing, we're gonna try to cover quite a lot of topics, and I guess you'll get some questions. So in the end, we will have a Q&A session. So do not hesitate to drop your messages in the chat, and we will walk through them in the end of the session. So yeah, I think we can get started. So enjoy, and please, yeah, be proactive. Ask questions if something is not clear. All right, I'm going to turn my video off just to make it a little smoother. And let's continue. So what is today's agenda? We will start from a very short introduction, basically why the modeling itself is important, and why the standards are getting more and more complicated. We will talk about the challenges in the steel structure industry, so basically common pain points engineers face and existing solutions, also their limitations, and then we will smoothly continue with some little bit more optimized solution, which we offer here at SDC Verifier. So automatic structural verification, multi-standard compliance, design optimization, and we will also walk through some examples and demonstration, step-by-step walkthrough. Yeah, and like I mentioned, in the end of this webinar, we will have Q&A session. Unfortunately, we have just 1 hour, so I hope to make it really fruitful and be on time with everything. So for those who don't know, here we are. Yeah, brief information about our company. So who we are, in fact, we are engineering consultancy service company and also software development company. We started many years ago as consultancy services company, and we have many engineers, a separate engineering department basically. And the core idea of the software development was that we noticed that a lot of engineering routine can be actually automated, simplified, and we can actually make engineering life better. So we came up with our own software, SDC Verifier. At this time, it exists both in standalone version and also as an add-on to popular programs like ANSYS, FEMAP, and SimCenter 3D, which was the initial idea, basically. So this is also an extension to this software as well. Also developed some other web-based tool, which is SDC SAM, that helps to maintain our structural health of our structural assets, basically. And yeah, so far we have more than 200 companies around the world happy, more than thousands of happy users, 3 offices in 3 countries, many years of experience in engineering, over 250 consultancy projects over the past 10 years, and many happy customers, which we hope will be even greater number. We are not focusing on one specific industry. We're involved in multiple industry, which makes us a pretty multi-industrial software development company, because basically at this point, I would like to admit that the topic of the today's webinar, which is the steel structure verification, is an integral part of every single industry you see here in the screen, whatever it is. Basically, whether this is oil and gas industry with this jacket structures, platforms, mud platforms, and many more, which you typically check according to AAC, API, Eurocode, DNV rules, etc. Or, for example, shipbuilding, which is pretty obvious. So you have many frames, longitudinals to be checked, and many other things. For example, according to ABS or DNV standards or more, or apparently heavy lifting. I think there are no more words needed, because basically everything is made of steel, and you have many standards you need to use, like FEM, Eurocodes, EN 13001, DIN standard, etc. It's also extended to civil engineering. Apparently, it's not just about the concrete structures. This is a lot of steel, steel plates, either welded together or bolted or riveted. So, such standards like Eurocode or ISO or other European ones, they are also taking place here. Same about machinery and equipment, of course, aerospace, and you have many structures made of steels, and that's the main, basically the key point here. But let's think about for the moment why accurate modeling and simulation are critical for steel structures. Because why do we need to model all these things, and why modeling part in our engineering daily routine plays a key role? I would like to start from a very typical calculation workflow of any project, let's say, because typically you start from type of calculations, right? You want to make decision, okay, I'm going to use hand calculation approach or spreadsheet or some program or extensive software solution or FEA method. But in the end, you need to build a model, you need to build a scheme. How do you see the structure? How are you going to simplify it? How are you going to account it for in the calculation? And only after that, you come up with the overall calculation scheme. How are you going to apply your loads, determine factors, etc. And only then you continue with calculations. And after receiving some basic forces, displacements, or stresses, you of course want to make sure that they are within the allowable limits. So that's why you proceed with verification and code compliance. But it's also not all, because after getting some results, you need to post-process them and make sure that they make sense actually. And life is hard, and very often you need to make changes to your initial design assumption or existing design, because it can be that your obtained values, they are out of the allowable limit. So you need to optimize and update your model. Finally, after doing that, you of course would like to report or document your steps in a certain way, or produce the drawings, or prepare the report for the client to get a final approval. But talking about the modeling, let's imagine for a second that the model you built is wrong. Basically, it includes mistakes. What happens next? Apparently, all these steps, they're going to be incorrect, because all your calculations do not make sense. Too many people, they keep fixating on the calculation stage, on calculation scheme, etc., but they treat modeling part as something not really, let's say not really crucial. But idea is that this part is definitely not less important, because if the model is wrong and you made this wrong simplifying assumptions, then of course the full procedure is wrong, and these all steps, they do not make sense. So building an accurate model and creating all those local components in detail, this is actually an essential step in our daily routine. At the same time, we have increasing complexity of standards compliance and verification. You see that everywhere actually. For example, when talking about the same DNV standard, this is of course closely based on the FEA approach, and it provides you with a clear guidance. How do you need to proceed? How do you need to build your model? For example, starting from global strain analysis, giving you some example. Okay, this is the the ship or cargo vessel, that it should look like that. And these are the requirements if you want to conduct a global strand analysis. If you want to go on with partial analysis, that's fine. You have separate rules for that. And of course, if you want to make sure that on a local level, the structure is still meets the requirements of the standard, you need to dive into even more details. For example, like with this opening and ring and the brackets welded, where you have to really have fine mesh following the mesh requirements, sometimes making it really fine mesh area, and yeah, extended this to the larger scale. So on the one hand side, we have basically FEA approach that is very often a complex procedure, but on the other side, we have complex formulas and complex rules. For example, like in this case for buckling check, because you have stiffeners, plates, girders, you want to make sure that the buckling risk is eliminated. So you have to follow clear procedures, complex formulas, which in combination with FEA approach make it really complicated, not an easy thing to solve. This is of course not limited only by the DNV standard, but widely extended to other ones, for example, like Eurocode, because the standard itself is not that easy. Although many people use it on a daily basis, but it's not that easy, as it has clear requirements for classification determination. You have those buckling curves, correction factors, these bending moment ratios, complex formulas. And this is even more, well, it's basically extended to even more checks. For example, when talking about fatigue. Yeah, so here are some examples from Eurocode, the N13001, and DNV, where you have to clearly follow SN curves and come up with the clear classifications, so notch classes, FAT classes, or characteristic fatigue strength to be accounted for in detail for every single weld. And then it's supported from the other side by the hotspot stresses. That is also in-depth FEA-based approach. That is not an easy thing. So on one side, we have modeling as a critical requirement to be followed when checking steel structures, because, for obvious reasons. On the other hand, we have increasing complexity of the standards. But why do we need to model once again these all steel structures in details? Why can we not use hand calculation approach or some nominal method? Of course we can. However, the complex side of this story is that we have many stress concentrations everywhere in the steel structures. So if it's not just a simple beam or simple plate you use to calculate manually, in other case, you have many stress concentrations which are hard to account for by manual calculations. You need to come up with all kinds of assumptions, and that forces us to use in-depth approach, like for example, finite element method approach. So, but how to get to this point, how to get this structure created? Because here we impose the other challenges, and let's talk about them a little bit more in detail. So to create the FEM model, basically we need to come to walk through certain steps. First of all, this is geometry. Why do you need geometry? I think everybody knows that geometry just helps you to create the mesh. So it's only helping you create the mesh, so elements and nodes, which is the only part analyzed by the solver. And it doesn't matter how accurate your geometry is. If your mesh is of a bad quality, then the model is of the poor quality. That's the standard solution. So geometry is just the backbone for mesh creation, which is of course the second part over here. And if we go to the mesh creation, that's also a tricky thing, because there are different solutions available nowadays, but this is very important to understand and to have all the tools to make this mesh at a good level. For example, in this picture, you see definitely unacceptable mesh. Yeah, so you have stiff elements, you have not enough number of elements along the edges, and that creates, of course, that all influences your results. You can have a better mesh, for example, like that one, but is it still good enough? Well, that depends on the area of interest, but of course, when we're focusing on this specific one, it's better, but still not the perfect one, and preferably you would need to have something like that. This is very much critical, and having this advanced meshing is also critical because it all impacts your results. Here is just a simple example. When you when you start from a bad mesh and ending up with a good mesh. So basically, in this case, you have 2.5 times lower stress level compared to the fine mesh quality for obvious reasons. And here, well, that's something average, basically in the middle, and but still around 30% less than the fine mesh. So advanced meshing is really required to make sure that your model corresponds, basically meets your expectations and also expectations of the standard. Because the same DMV standard I was talking about that clearly regulates, for example, the mesh size, and you have to follow. Same Eurocode standard, although it's not officially released as a separate standard, but still you have a technical committee that released a paper that is soon going to cover a big part of the FEA approach as well. So we need to get more harmonized rules for all of this to make sure that we are moving in the right direction, of course. But making geometry and mesh does not make your model complete, of course, because you still need to come up with the loads and the boundary conditions. And when it comes to the loads, they can be really tricky. For example, like in this case, you have an oil and gas platform, you have wave load that is occurring from different directions, that is uneven, as well as the wind influence, for example, that is very often is not constant over the height of the structure or the buoyancy load. So these things are also making quite a challenging part when it comes to the modeling. And of course, after that's done, we need to put boundary conditions on our nodes to make the model calculatable. But is this the only challenge? Of course, no. This is just related to the modeling part. And when it comes to the verification, you would say, all right, we have some traditional methods which I'm good with. I'm fine. Basically, everybody's using hand calculations because you want to support your FEA results with manual calculations, with some internal procedures or spreadsheets. That's all fine. But when talking about manual calculations, what is the biggest risk? The biggest risk is that one thing, it's hard to visualize it. Second thing, it's easy to make a mistake, right? Because it's not automated. You would say, all right, we have internal company spreadsheets we have been using for years, which is also good. However, does it completely eliminate this risk of error? Of course, no, because it's still requiring a lot of input data, some basic forces or displacements, also input parameters. And that's something, it's definitely better than just the hand calculations on paper. Well, also not always, I would say, because it depends how serious your task is and how quickly you want to get to the answer. But I think also one of the drawback of this is that this is really limited accuracy. That's one thing, and this is hard to visualize. Yeah, along with the prone to human error and efficiency. So this is something we would like to make actually better. And this is one thing, so overall method. Second thing, when it comes to the overall code compliance. When you go to a code, any code, again, regardless the industry, you typically have the predefined number of load scenarios you have to take into account, right? Whether this is Eurocode standard with all these things, or EN 13001, or DNV, whatever standard you use. Idea is simple. We have multiple load categories. Okay, permanent load, variable load, etc. You have multiple load positions, most likely, because even the same Eurocode, you might have a live load, equipment installed at different spots, live load from human, or live load or different load position, for example, when we're talking about the crane or lifting appliances. And yeah, that's another thing. Load directions. You can travel in different direction. That's posing inertia force in different direction, wind load in different direction, wave load, etc. Different dynamic factors, different partial safety factors. And if you come up with the matrix, you end up with hundreds and thousands of load cases. Does it make your life easy? Well, of course, no. So this is something that is really challenging to accurately, let's say, account for in our daily routine. Next thing is the standard requirements themselves. For example, we have many structural checks to prevent issues, whether this is a strength check, fatigue check, residual lifetime analysis, deflection check, beam buckling, plate buckling or stiffener buckling, joints connections, bolts, rivet, weld capacity, any kind of checks. And you have, of course, many codes to use. And just imagine you have all this list of checks, you have different codes, and you need to use multiple codes, multiple standards for the same structures at once. And that is really posing a big challenge, because on the one hand side, you have many checks, many complex procedures. On the other side, you have also some standards you would like to combine. For example, I don't know, the same offshore industry. Yeah, so you want to use API in combination. Yeah, API, let's say for tubular checks, but AAC for other members, or joint check, let's say according to API or the same ISO or NORSOC, and then the other ones for different things. So this is really tricky part over here. And just imagine what happens if your design is not within the allowable limits, because you might have some strength problem, fatigue problem, bolt check, buckling problem, and you need to solve it somehow, right? So how do you typically start to do that? You got a problem, you checked multiple options, leading to some FEM model updates, obviously including your mesh. You need to recalculate your model. You finally found solution, so you are about to prepare the report for your customer, and then you get a request. Hey, can you quickly change the plate thickness or cross-section loads, weight, whatever it is? Well, that's a good question, because it also means that all this process should be repeated again. And that's another challenge. How can we adapt ourselves to quick changes, basically? So there are, of course, existing solutions, but they also have limitations. For example, you might use some custom API integrations and external scripts, because you don't want to do all the stuff manually. But yeah, one thing is that it has limited applicability, so it's not fully automated thing. It's still faster than manual work, but time consuming, because you also require additional maintenance for this. Very frequent situation is that people are using multiple programs, because one program is not enough, which still makes sense, of course, but there are a lot of drawbacks actually, because you frequently require your FEM model updates. That is, I think, also a very time consuming part. And all these import and export things, that is all leading to reduced performance. What do I mean here? Let's say you have a global model, right? You are verifying this for different things. Then you got a detailed connection you want to verify. So you do export of this connection, geometry part, to some other software. You analyze it, you post-process the results, then you need to import it back or account it for somehow in your verification workflow, or do another way around. For example, you do something, I don't know, in ANSYS, you need to verify it, you use SACS, so you export this to SACS, you got some results, you need to account them for in ANSYS back, because it turned out that it's not passing the rules, and then you run in a circle. And that is all, of course, requiring a lot of time and leading to the reduced performance. So this is definitely not the best solution in the market. And the best solution, in our opinion, is, of course, when you have all-in-one software solution. Let's say one software for everything. So it helps you not to jump from one thing to another, making this completely mess. And that's where basically SDC Verifier popping up. So what you see in the middle of the screen is just a standard workflow. For those who don't know it yet, how does it work? Basically, you start, of course, from your FEM model, from your simulation, um, build it from scratch or import or whatever. You create a lot of load cases. You enable structural checks according to multiple standards through structural verification items. If something is not passing the rules, you have optimization module that helps you to quickly update your design and find optimal solution. And you generate the report. And what is cool to see is that these two arrows, actually, because they are added here for a reason, if you got any changes, the same plate thicknesses I mentioned or whatever, you just need to update the model, recalculate it, and you can go straightly to regenerate your report. All those steps intermediately, they will be repeated automatically. No need to do it over and over again. Yeah, I mentioned at the very beginning that, of course, we have, I'm going to talk about some features and cool things to automate, but they are available, keep in mind, in as a standalone software and also as an add-on to FEMAP, SimCenter, and ANSYS. So when talking about this workflow, yeah, I'm going to remove all this nice painting. About the modeling part. So what you're gonna do, this is how the interface looks like. So you create geometry, you create a nice mesh, you create all those specific loadings because they are really, really nicely automated, and you do it efficiently. So there is a lot of features to create your model efficiently, starting from simple beams, plates, solids, whatever you're gonna use. And that, of course, helps to prepare a nice backbone for your meshing. And talking about the meshing, you have a very wide range functionalities, also involving a meshing toolbox that allows you to automatically create a nice mesh quality. So not those pure element quality, but a nice mapped mesh, for example, which you can see here as an example. Of course, this is all applicable to all types of elements. So 1D, 2D, 3D, doesn't matter what level of complexity you have. We went even further and we also extended the modeling part to the parametric modeling module. For example, like for this crane modeling, where you just have to fill in your dimensions and the model will be done automatically. So that's a first option. The second option, when you can just use the file to model import, for example, it's compatible with your template file. Let's say you got some Excel files with predefined cross sections or materials. So you basically have your model described. You can import that way too. You might say, all right, but what if I have already existing model? Why do I have to create a new one from scratch? For example, I have been working with ANSYS, or I have some step file I'm going to use for geometry, or I have some Tekla model, StatPro, whatever you use. That is also fine, because basically our software is compatible with all those format files, and basically in two directions, because it also means that you can use your ANSYS model in SDC Verifier and SDC Verifier in ANSYS model. So it works in both directions. And well, basically, you can try it out yourself, how it works, and register for your free trial right now. You got a link popping up in a chat, so you can proceed with that. After creating the model and mesh, you of course need to apply some loads. There are different ones, so you can apply it in different manner, but those outlined over here, they're really automated, because wind load, Beyonce, or wave load, these are really painful points, let's say, in terms of how to apply that to finite elements. So our software helps to automate it. Yeah. After making sure you got the model solvable, you can of course proceed with the load combinations. And load combination, this is something I mentioned at the very beginning. Regardless of the standard, you have to prepare hundreds or even thousands of different load cases. So how SDC Verifier solves this thing? Most of the time consuming part is, of course, solving this with the solver, right? So, but idea is that how to read it. Let's say I have the load set 1 and I need to combine my own weight with some wind load, with some movements, and that is just one load case, including some factors. You have different ones. So we call it individual loads. So this is just one individual loading. Either this is a known weight or live load. And then after solving them, we have a linear combination of these loads to create the load sets quickly, either from your Excel file you got used to or in an automatic way. I'll come back to it in a second. And if you want to quickly review results and make sure that you have or don't have any problems, we call it a load group. So basically it shows you absolute maximum over all load cases or loads included in this thing. So in short, if you got 100 or 200 different load cases, including wind influence, and you want to get quick understanding what's going on with your model, you get one picture for every single finite element. You get absolute maximum results from all load cases. So you keep in mind that it does not happen simultaneously as a one load case. It's impossible, but you have kind of envelope of set of results that helps you to get an idea if you have any problems or not. So yeah, like I said, you can just copy and paste your old school template prepared in Excel file and get in some nice matrix, or you can create them automatically in our software. For example, using the same EN 13001 Eurocode or ASCE standard. So how it works, you have different load categories. Even if you have, by the way, these different positions I was talking about, this is also possible. You just specify that this is position, like for this crane result. And that creates load cases for you, specifying all the factors according to standard. Also cool advantage is that you don't have to open your standard anymore to find out about any factors to be used, because you have here an information button. If you press it, you get a dynamic picture appearing, for example, according to Eurocode. So you see directly, okay, these are my gamma factors or dynamic factors, and dynamic factors are separately shown in a table with recommended default values, but you can, of course, adjust it according to your needs. So how it works, you just go to setup window, right? You have some list of loadings, you set up some category, but of course you need to choose the standard first. So you say, okay, this is permanent action, acceleration is my whatever, leading accidental action, and then we have some side loads. This is my variable action, and the wind load I want to set up according to Eurocode, that is wind load on buildings. So once you click OK, you get all the load cases created automatically, you see, on the left-hand side. And if you edit that, you see all the factors are accounted for by the software. So you don't have to take care much about it anymore. This is all done for you. But of course, after applying all these things, you need to solve it. And when talking about finite element solution, SDC Verifier is backed with SimCenter Nastran solver. Well, this is actually a widely known solver around the world that was developed by NASA back in the days. So this is the core solver in SDC Verifier. So once you got some basic results, stresses, displacements, strain, whatever, some forces, you want to go with checks according to rules, right? But here is a tricky part, because all those nice finite element models, they are not structural items. These are just finite elements, a set of finite elements. And structural items is something different. So beams, columns, plates, welds, etc. This is something you have to recognize. And this is what we actually do. So starting from joints, beams, welds, stiffeners, plate fields, or girders, basically this is all recognizable. All you have to do, you go to the software, there is a recognition panel over here. all these things can be recognized separately, or you can recognize them all at once. You just get the full list of things recognized in the end, you see, and you can go one by one and check how it looks like. For example, joints, and you plot the joints like this. Yeah, so intersections between your beam members, set of elements. You plot them and you see that, okay, this is nicely highlighted with the colors, taking into account the stiffness of different components. Sorry, it got yeah, my PowerPoint got slowed a little bit, so that will take a couple of seconds. By the way, while it was opening, I think you noticed that there are a lot of different items over there, and all those items. This is not just the recognition of, you know, of structural items, but also determination of the of their input parameters, for example, beam buckling length or dimensions of your shape, and etc., etc. Yeah, it seems that I have to quickly restart my PowerPoint, so sorry, that will take a couple of seconds from my side. Okay, now you should see my screen again. I'm gonna get to the slide where I stopped, and it was somewhere around here from current slide. Oof. Yeah, so I was talking about that, about the recognition. Yeah, so we can recognize all the things at once, but after I'm going to plot one of the things, you will notice that in every single window, you have the input parameters, and these input parameters are determined also separately and accounted for in the standard. For example, type of your joint connection, what is HORT, what is brace, or here, what is the length of your member, beam buckling length, what is the buckling factor for buckling checks, right? Or when talking about panels, okay, what is the widths and lengths and the slenderness of your plates, plate thicknesses. For stiffener, same thing. When talking about weld, you have a separate thing for weld strength settings. You know, when you specify weld size, the approach you're gonna use, etc. Or for example, set up a hotspot method. For connection check, okay, if you have tube-to-tube connection, or if you have I-beam connection for connection check according to Eurocode standard. So all the things, they're automatically accounted for in the checks. You don't have to care about it. It's not just the recognition of members themselves, but this is also recognition of the parameters you would need for verification. This is, of course, applicable not just for simple structures like this, but also to complex structures. For example, like in case with the ship where all the welds are recognized. Or, for example, extended to the solid models, because for solids, this is always a challenging part to recognize your welds. However, software does it successfully in this case. After that, after you finished all your recognition, you of course would like to proceed with the checks according to standards. And yeah, we have very extensive database of the standards. So starting from, I don't know, Eurocode, same DNV standard, many versions. For example, when talking about Eurocode, this is buckling, welds, fatigue, bolts, even fire design standards, so fire influence, plate buckling, connections, so many different versions, and this is what we just call with this one icon. AAC rules, offshore standards, FKM, all the things they are available. And the biggest, one of the biggest advantage is that all those standards, they're completely open. So you can check the formulas, you can preview them, and you can modify them. For example, if you came to conclusion that you don't like rules of the I don't know, Eurocode fatigue or strength check standard, you can convert it to custom standard, go to the formulas, modify formula according to your internal company's rules, set the password protection, you can store it to library and share it with your colleagues. How cool is that? And then you get a unique standard that is adjusted according to your company needs. Moreover, you can create your own checks. For example, you calculated stresses and you have no standards having such rules because you want to use different safety factors. For example, yield over the safety factors that is allowable stress, and then stress calculated over allowable that is utilization factor, and it should be below 1, yeah, below or equal 1. So you can write it in a couple of seconds and you get a nice picture of the check results instead of the simple stresses, right? Because also for shear stress, for example, this is tricky part because it has different safety factor. Or another example with boats, same idea. Yeah, but regardless the check, every check is supported by the different representation of results. So for example, like this plate buckling rules, which is supported by the a nice plots, also very extensive tables. So in short, any single parameter you see in the standard, whether this is critical stress, buckling state, or some outcome that can be reported in the tables. Same goes, for example, to fatigue and weld checks, which is, by the way, based on the ascent curve, so Palgrim minor rule with the real stress history parameters. And you can assign in detail all those notch classes, and in the end, that gives you a very nice and accurate representation of results, focusing on the stress concentrated areas, specific also in the welds, yeah, which are prone to fatigue, that in the end result in the well, pays off in the end actually, because there's also a real picture of crack of over 20, 30 centimeters, I do not remember. That was all the time overlooked, and yeah, after analyzing this with the software, turned out that there is a crack inside, to which nobody had access back in the days. Or the same goes for the beam buckling. So any single check basically can be explicitly reported. Moreover, you can get a full calculation history. So every formula, for example, effective section modulus, you see the formula, you see the values used in that formula, and how did you get to a certain value. So full extensive calculation procedure that can be exported to Word document and shared with your, I don't know, quality control department within your engineering department, for example, for checking and verifying if the workflow is okay. That is essential also for double checking yourself, not only just for third-party reviews and submission for certificates. It's even more tricky, like I mentioned before, because can be that you have, for example, something like that, yeah, structure, which you need to verify using different rules. For example, top part, you need to check for plate buckling and stiffener buckling according to DNV. Those supports AAC. Then you have some tubes and joints. You want to use API, NORSOC, and ISO standards to verify them, but those supports at the bottom, you want to check according to Eurocode. Huh? How tricky is that? But this is all manageable. That's just a matter of number of standards you're going to create in the software. For example, like here. Moreover, a lot of the standards directly allow you to use some cross references. For example, when checking something according to ISO, so tubular shapes for offshore structures, you have an option to use AIC for non-tubular shapes and vice versa. When checking something according to AIC, you can use API, for example, for the tubular shapes. And then you get one picture directly accounted for different rules of different standards. Moreover, you can create a comparison standard. What do I mean with this? I was talking about the before mentioned API, NORSOC, and ISO. Yeah, pretty comparable standards, I'd say. So what you can do, for example, you want to take into account only the highest values from each of the standard. So you create this comparison standard at maximum parameter. So you take into account all three together. And what you're going to report and plot only absolute maximum results among all of these standards. Yeah, and that is also a huge time saver in case of you need it. But let's ask yourself, what if the design exceeds the limits or fails to comply with standards? What we have to do? Do we have to run through, dozens of different iterations, guessing ideas, and so on? For that purpose, we have a separate optimization module, for example, like in this case with beam members. So if you see that your structure buckles or does not withstand bending forces, whatever, what you do, you have extensive library with all the shapes. You select shapes you're interested in, for example, different ones also, some APE or UNP sections or IPE, and it gives you optimal results among all of these. So you just select list of shapes, click OK, and go drink coffee. That's what happens. In the end, you get a nice picture because it's not only calculating those options automatically, but also determining the most optimal result. Yeah, so you are not wasting your material, putting a significant safety margin, but also you stay within the limit. For example, like over there, you had buckling issues, which obviously became okay with the help of optimization. Same goes to the plate buckling checks. For instance, when you need to increase plate thicknesses to prevent buckling, or replace some stiffeners, or, for example, the weld capacity is not enough. So you need to go, I don't know, from fillet weld to full pan weld, or to increase the size of your weld. This is all doable and possible. And after it's done, basically you can generate a report as promised, because we have already some predefined reports you can use on your own, or create your unique report just by dragging and dropping items. Yeah, that's how it looks like inside basically the interface. So you can insert any kind of information, starting from materials, properties, highlighting with nice tables, etc., inserting results, graphs, tables, plots, some post-processing tools to find out how it works. You can even link existing documents which are not part of this report. Yeah, and in the end, you get hundreds and thousands of generated pictures automatically and sorted by bookmarks or chapters in your document. But okay, all right, you went through all this, and at the very beginning, I was talking about the last minute changes. You need to change plate thickness, verification. Do you need to go through all the steps again? And the good news is that no, the entire workflow is fully automated, and that's what these two arrows is about. So you need to update your model, recalculate, and just regenerate the document that is already stored. Moreover, if you have even some typical projects, for example, I don't know, you got 50 beams with the same logic but different shapes or cross sections or cranes or whatever you have, you can run API console and come up with some script. For example, I want to open existing project, yeah, a template, remove all load cases, import another ones, create load group to get results in one picture, recognize welds, check them for fatigue, generate report, save project, close. That's it. So that's, well, we see, and also from feedbacks from our clients, that saves you enormous amount of time, yeah, and increasing efficiency of the workflow, leading to over 50% of the time saver. And the best, well, let's say the best driver and the motivation for us to develop in this direction is, of course, the feedback from our clients, like this one, for example, from Olses, who managed to get over 4,000 pages of results for 22 models reports just in 2 days, automated, which saved them a significant amount of time. So just to sum it up, a lot of text, but still accurate FEM modeling is critical. Yeah, we have complexity of standards that is only increasing. Traditional methods are fine and they will always take place, but they are prone to human error and inefficiency, so we have to combine it. Code compliance is complex and time consuming, that is obvious, and using multiple programs, that is make it better, but still that is still time consuming because you have to jump from one export to import and so on. So having solution all in one is of course definitely the best approach, because it automates your structural verification. In our case, that supports huge number of standards in building library. We have optimization modules, so you don't have to struggle anymore with guessing some options which might not work in the end. You can quickly generate report, allow last minute changes, as you don't have to repeat it yourself manually again, because full workflow is saved, and that saves you a lot of time. Depends on what you're doing, but definitely a lot of time. So that's briefly what this webinar is about today. I hope that yeah, that was pretty clear. Despite I got my PowerPoint a little bit slowed down, but still we have still some time. I think 7 minutes or something to talk about your questions and answer them if you have any. I'm gonna go check the chat if we have, because we do have some. Please remove the small window on the bottom of your screen. It's a bit pity that I just noticed this message, but yeah, from the welding list, recognize, how do you identify what lines is in particular one on the screen? Andrea, what did you mean with that? Welding list, recognize, how do you identify what lines is a particular one on the screen? Okay, so what weld corresponds to the weld in a model, you mean? Yeah, correct me if I'm wrong, but if that's it, if that is your question, that's pretty simple. I will show it to you. Okay, I think I solved. I solved the problem. Why? What was going wrong with my PowerPoint? I put it too big video size. But what is the idea? You can plot those welds and you can pick them up directly from the model. You don't have to guess what is shown there. So you have a long list, of course, because very often you have thousands of welds recognized in the model. But idea is that you see on the screen something, you can pick it up, and that is highlighted in the list of your software. So that's how can you see that. You can also plot them with ID, with length. So there are many ways to figure that out, of course. How does someone get a training using SDC Verifier, and what is financial implication? Well, we have we can provide training both offline and online, so either in your office or online training. It depends how deep you have a training, but you can also contact us at support@sdcverifier.com and we will share some prices, because idea is that we're trying to align with unique needs of the client, because you probably have some unique pain points, unique projects you want to solve and adapt all these rules specifically to your projects. So we take a list of topics we want to cover, and that might take different amount of time. Some people need, I don't know, several hours because they know basically everything, but some of them several days because they want to really speed it up and start quickly using that. So please contact support@sdcverifier.com about the training. Mano, I want to cover a 3D vessel geometry to plates, convert a 3D vessel geometry to plates, also for the bolt profiles. Is this possible in SDC Verifier for ANSYS? Yes, it is possible, but if it is SDC verifier for ANSYS, SDC verifier, then yeah, because what you have to do in ANSYS is that you're creating your model in space claim and ANSYS mechanical. So basically, most of the modeling features, if we're talking about ANSYS, is related to ANSYS, but still SDC is taking part in all this pre-processing concerning the load cases, loads, etc. Everything except for the model creation itself. But whatever you do in ANSYS, that is extracted and stored in SDC Verifier, so you can read it, of course. In standalone version, there you have a wide range of functionality for directly modeling. Yeah, because ANSYS uses its own space claim, and yeah, that's the way it goes. OLXC, can the post-processed FEA results, Bucklin, Fatigue, SDC verifier assembled in the report be directly used by approval by classification societies, DNV, ABS? Oh, actually, it's a good question because the answer is definitely yes. When it's coming about classification societies, for example, DNV, you set up the meeting and they definitely want to review your design calculation or structural calculations, and that follows the full procedure. So you have to explain basically every single detail, and our software is open for that. It's not a black box because you can directly report every single component, so to not make it a black box but fully transparent document that is directly accepted and can be used for approval. So answer is yes. Can you search through all the codes? Perhaps search for minor rule or fatigue? Can you search through all the codes? Search for minor rule. Not sure what this question is about, but minor rule, yes, it is accounted for in fatigue in our approach. So yeah, in most of the rules, basically, whether this is DNV, Eurocode, EN 13001, etc. So yes. Thanks, Roma. Very insightful. What the possibilities are. Talk to you later. Greetings. Okay. Thanks, Rene. Alexei, is there anything additional should be considered when preparing results using SDC Verifier for class approval? Well, it depends basically what are we going to approve, but different societies, they have different requirements. So that is, of course, should be agreed first of all with them. But I can assure you that SDC provides with all the functions and all the possibilities to get that in the document. Because again, if it's a new design, for example, to certify, that's one thing. So you definitely have to have the fully transparent document, and that's what you can do with the reporting, because every single procedure, step, input data, output sets, that is all transferred and can be easily generated. If it's, for example, some significant change to the existing structure, you also have to discuss it with the society, because it can be that recertification is not necessary, but you only need to get an internal approval from society based on some other checks. Yeah. So, but in general, you have full set of possibilities to submit that for the approval. John, I meant search through the standards, not codes. Okay, but what kind of search? What are you going to search through the standards, John? Because standards, they're basically implemented as it is, and can you please be more specific in question? What is the main intention here? What you're gonna search? How hotspot and RADA approaches included? Well, the hotspot method is implemented according to IIW standard, so we followed those reference points, and it is included in every single standard. So it's up to you whether you want to proceed with the nominal stress approach or a hotspot stress method. There is a checkbox, so you can use basically both if you like. But in general, this is according to IIW method. I meant standards. Very interesting. Thank you for presentation. Meaning find all standards that deal with fatigue. Okay. This one I get it. All the standards you see in the list, which include fatigue, they typically have it. However, that's a good actually question, because pretty recently we were talking about to add some kind of a filter between the standards. So not just in help section, or not just, sorted by Jira codes, DNV, and so on, but sort them by categories. So fatigue checks, and then you get full list of standards having fatigue, or buckling checks, etc. So this is definitely on our list. We're going to go, but typically when you just go to the menu over there, you have a ribbon. I'm going to maybe drag it. Just a moment, because I have something open. For some reason it's blocked. But what is the idea, John, is that you have directly specified, for example, like for Eurocode, this is buckling check, this is fatigue check. So it's included in its name. So you're not going to be confused on this. But filtering, this is something for us to go, definitely. All right. I think I answered most of them, but I also see more questions. What's the latest version of SDC Verifier, please? The latest version is R1 to 2025, but we're going to release soon, I think this month, the latest version. So it's going to include a lot of new features, bug fixes. So please keep updated. Okay. I hope I answered all the questions. Otherwise, you can also unmute yourself and ask them directly, because I see this is, yeah, seems to be full list. More questions? Yeah, definitely 1 hour is not enough to cover everything. So I try to include most of things that might be interested for everybody. There are much more to test and to try, but I think the best way to do that, of course, try it out yourself. Just click here and there, and you see what works best for you. And yeah, like I mentioned before in answering previous question, that if you're struggling with something, because I can imagine that everything is new, basically. There are a lot of features, so it's easy to get lost. And you have different projects, whatever, depending on industry you came from. You can always contact us, and we can discuss your specific problem, specific project, and try to adopt all these rules according to your needs. Because like I said, this is a multi-industry software. It's not focused specifically either on, I don't know, jackets, platforms, or cranes, but that includes all the features to be able to solve everything. And the question is, do you need, what do you need specifically? So contact us, and we'll be happy to help you. All right. If there are no more questions, then appreciate you joining today to this webinar. Thank you again, and see you next time. A good one. Thank you.